Hello everyone, thank you very much for joining this live event. We discussed today more about microservices and we get into how to keep your data consistent when you have separated the persistence layer, because that's one of the things we discussed in the previous episode, is that when you use microservices you separate the persistence layer as well, and now you have only one responsibility per component, which includes its own persistence layer, which gives you some nice opportunities like having a polyglotic environment, but comes with different other problems as well, that other concerns that you need to address. And one of them, and maybe the most difficult from my point of view, is keeping the data consistent. If you're watching the event live, don't forget that you have a live chat there, so you can ask me questions directly in the live chat. Or leave comments. If you don't watch the event live, then you can still ask questions in the comment section of the video, and if you want to stay in touch with me, you find me on Twitter and on LinkedIn as well, so we can discuss there. If you'd like, follow me and we continue the discussion. So with that being said, let me share you my screen, because I didn't show you my screen. And from now on we should have a look on the whiteboard here, otherwise it makes the things more difficult to understand. You have the schema we've worked on in the previous episode, and you can see that we have here some microservices represented using some squares, and you see that each service might have its own persistence layer. I say might have because it doesn't necessarily need to have a persistence layer, but if it has one, then you definitely don't have anymore the case where multiple services connect to the same database, because in terms of microservices you have to separate the persistence as well, and you have to make sure that each service has only one responsibility, which again I want to stress the fact that it doesn't mean only one thing. It can be more things that are highly coupled together, and they represent only one concern. Cool. With these regards, let's step directly into the things you are interested about today, which is how do we keep the data consistent if we have a use case spreading through multiple services. In the previous episode, I only tried to address what a microservices system is, but now we have to detail some of the things and some of the concerns. And again, this is probably the most difficult. How do you keep the data consistent? Let me tell you more about what I want to say by that. First of all, you know what a transaction is. A transaction helps you manage your data and keep it consistent by its atomicity characteristic, which means that you have multiple operations mutating data, but if one of them, if at least one of them fails, then we just roll back everything. We make sure that we don't do any change that was previously done by any operation in the transaction, and we keep the data the way it was when this transaction started. So a transaction, first of all, helps us keep the data consistent. But the problem is that you have a very easy way of implementing transactions when you are within one service, because you have now lots of opportunities. You can go low level, or you can have even a very high level implementation, such as the one that a nice framework gives you today. Like in case of Spring, you only need to add an add transactional above the method, and it's already wrapped in a transaction by Spring, so you don't even have to do a lot of things for that to work. But the trouble comes when you have a microservices architecture, because now you have multiple databases and you have multiple services, and sometimes use cases are not solved by only one responsibility, but they need to have you need to have multiple responsibilities communicating one to the other, and each of these responsibilities mutating data in their own database. Suddenly you don't have any longer the possibility of very simply adding an add transactional and that's it, because now you have multiple transactions. So say you have this case of only 2 services. To make it simple, let's just consider 2 services. I always like to go with the simplest scenario as possible, where you have a use case spreading throughout 2 services. They both have their own, of course, persistence layer, and they both need to change something in their persistence layer. And I will take a very simple scenario. You buy a book, you have a capability on a website where you buy a book or a product or whatever you want to buy. The inventory decrements, and then the payment is executed by a different service. So you have the inventory management, say service A, and then you have some other responsibility, the payment, let's say is the second responsibility, and our full use case, for simplicity reasons, is only composed out of these 2 responsibilities. But what you have to observe is that both of them change data, because here when you buy a book or a product, it has to decrement the inventory. So say you have 10 books, one of them is bought, then you need to have in the inventory only 9 books further, because one of them has been taken. And then you have a different responsibility, and you decrement the inventory, and then you have the payment. So whatever. Anyway, in this case, we do consider that both of them need to happen. Because in some cases, architecturally wise, it's a better decision if you can have a look and see if you can't rearrange those responsibilities so that you don't necessarily have to distribute somehow the transaction. So let me give you first of an example of what you need to take care of before thinking about distributed transactions, because as I've told you, I think I've told you in the previous episode, I do always prefer to avoid distributing a transaction if I can. Sometimes inconsistencies in the data are accepted, and always we need to think about whether we really need to distribute a transaction because we care about the possible inconsistencies in the data that might occur, or we can live with them. Because if you can live with them, trust me, it's better live with them than try to implement a complex scenario for distributing your transaction. In this case, so I have the inventory is getting decremented, and then the payment is being done. In this case, what we would like, if the payment fails, which is something that happens here in service B, is that the inventory doesn't decrement. Or we can have the situation the other way around. We make first the payment, and then we decrement the inventory. And then in this case, you will see that in such a scenario, it's maybe better that I go with the other way around, where I say I first try the payment and only then I decrement the inventory. So I do decrement the inventory only if the payment succeeded. So in this case, you see, you might not necessarily need to go with a distributed transaction for the second scenario. So in this case, if that was a real application, a real use case I would have to implement, then I would really take into consideration all my possible choices. And that's my advice for you, is don't stuck on only one view. Always think which are all your possible choices, because sometimes you will find out that you have multiple solutions for the same problem, but one solution is easier to implement than the other. That's the first thing you need to think of when you have such a case before going into over-engineering your application. A rule of the thumb for me is always simpler the better, from multiple points of view: testability, security, maintainability, faster to implement as well, so costs reduced. So it's always good to think outside of the box and see that all the solutions have all the problems have multiple solutions, and sometimes the first one you can think of is not necessarily the best one. But now, for the sake of the example, because we want to discuss distributed transactions, I will consider that we do decrement the inventory, and then we make the payment, and the payment can fail, and then what do we do with the inventory? Why do we have this question is because you can have here, say, this is called TA, let's call it, this is the name of the transaction, and the problem comes from the fact that in B, you have a different transaction now. So you don't have any longer the possibility of simply rolling back what you've done, because being different services, now it's a lot more difficult to do that. So that's why now we get into this situation, because when you say you, in this case, decremented the inventory, and you delegated next to the payment, then maybe the TA transaction committed already, and then the inventory is decremented, and then you try to make the payment somehow fails. And what do we do now? How do we roll back something that has been already committed? It's not possible on transaction, because from the transaction definition point of view, the equivalent of the commit operation is when you say things are persisted. Things now are persistent, and you cannot roll them back. So you need to find alternatives for that. You either don't commit up to the point when you know that everything happened okay, or you try to implement something, some other way or some other mechanism that allow you to revert what you have done. And both solutions, both of these are solutions to the problem. So either way you choose, you can either wait and commit whenever you know that everything worked correctly, and that's what we call a distributed transaction with a two-phase commit. You wait for everything to be committed, to be confirmed by all the services, and then you do the commit. Or you have a scenario where you revert something that you have previously committed, and that's something that we will call from now on a Saga pattern. So because theoretically understanding what a distributed transaction is, it's simple, at least simpler than the Saga pattern. I would like to start with the Saga pattern first and discuss it and tell you how and which are the possibilities to implement this kind of pattern that allows you keep your data consistent in such a scenario. Of course, again, this scenario is a very simple one, and it's basically one that is avoidable in this case. I'm aware of that, but again, it's just for my example sake, and to be simple, I keep this example. We can just think that this is something we can't do another way around, and let's say we've heard that we have this kind of approach called the Saga pattern, where you can use some reverse operations to undo things that have been done in case not all the steps of a specific use case work properly. So, because that's basically what this pattern is all about. So in my case, I do have here, I decrement the inventory. So I do decrement the inventory in service A. This is the operation which is part of my use case, and you see that's a modification. I do change something. I change the amount of books or of products that my service maintains in its database, and then here is the payment. So here I make the payment. So the idea is that it's basically very simple from the point of view of two services, and you will see that you'll clearly understand it. But trust me, it goes much more difficult with the number of services. So when you have the more services you have, the more responsibilities are connected within this use case, the more difficult will become for the Saga to implement. So should we use pessimistic locking for distributed transactions? Let me first take them step by step, and I will first now try to explain Saga, and then I will discuss more about locking as well. So I will skip your question now, sorry for that, but I want to focus on only one thing at a time, so I promise I will answer you later for that. So here we have decrement the inventory and make the payment. So the problem is basically that making the payment can fail, and then you have already decremented the inventory. So how do you solve that? The idea is very easy. For any kind of step that represents a change in the data, in your use case, you need to have a revert as well. So in my case here, say I have making the payment that can fail. If it's the last one here, then of course in this case I know if it fails I don't have to undo it anyhow for anything that would come later, but for anything that it comes earlier in the use case, like the decrement of the inventory, then I should also have a reverse operation that's incrementing the inventory. So increment the inventory. And what happens is that now we have two alternatives, as I stated at the beginning of this lesson, of this episode. When we discuss Saga, we have the possibility to create a choreography based or orchestration based. So both are very similar approaches. They rely on the same kind of logic, but in the case we choose a choreography approach, then what differs is that you don't have any central point, any manager of the communication. You simply have the services communicating one to the other. So in our case, simply imagine a scenario like this. If B fails, then it simply tells A, hey, I did fail, now you should roll back as well. And if B fails, then B tells A, you need to roll back. A applies the operation that represents the rollback for that specific first use case mutation operation it had executed. So then if the payment didn't work, then A simply increments back the inventory. So that's basically it. But now I took only two services again, which makes things easy to understand. Imagine, however, if you have more than two services, you might have 5 or 6 services, it is a little bit more difficult. Some of the operations are not necessarily only changing like a number, like I decrement the inventory and then I increment it back, which is the case here again as part of my example to make it simple for you to understand what a Saga is, because then you can have more or less complex scenarios of what a Saga is. The idea is the same. But think about a real world scenario where things are not that simple anymore. Then simply a simple operation like this is not possible. Then an undo of a previous operation might imply more changes. And in that regards, theoretically, if you correctly separated the responsibilities, then the theory says that you should have also a small number of changes or less complex number of changes for each service. So creating a revert operation shouldn't be that difficult. My experience says that an ideal world doesn't really exist. So in a real world, and not in an idealistic one that you find in books, things like this are quite difficult sometimes to implement. But the idea is the same. So you have the operation, you have the revert operation. If one of the next services fails, it just go back to the previous and it tells now you should roll back. And then the other one, say it's a longer chain, it goes back and it tells to the others you should roll back, and so on and so forth. If you have this kind of choreography approach, then you don't have a central point, and the services simply communicate one to the other, telling the status. So if I managed or not to do my work, if I didn't, then you who previously managed to do it, you should now roll back because you committed your transaction. And if you keep the data the way it has been persistent, then at the level of the whole system, it isn't consistent anymore. Or you can choose to have an orchestration, which is basically the same thing, but in case of the orchestration, instead of having the services communicating one to the other, you have a manager that tells everyone what to do. So you have a separate service that manages your Saga, to whom all the other services communicate what has been the status of their execution, and then the manager, based on what messages it receives, it orchestrates the services in the Saga, telling them what to do to revert or not the changes of that specific part of the use case. So pretty simple, isn't it? It looks, at least in theory, to be pretty simple, because either way you choose a choreography or an orchestration, mainly in an implementation, it relies to having some message broker with some queues or topics that you use to communicate the statuses. Yeah, it's just a matter of if you would like to have, say, central manager of the Saga, or if you want to leave your services communicate one to the other. But again, even if it looks simple, so I still do recommend you, as I discussed at the beginning, when you have to implement such a thing, even if there are two services, it might get more complicated than you expect in terms of implementation. And rising the complexity of your implementation is, of course, something that you sometimes need to do because it's a must, but if you can avoid it, then it's better to avoid it. And trust me, over-engineering is maybe one of the biggest sins in software development. You usually need to keep your application as simple as possible. Is this manager a singleton? I mean, every request should see the same manager, right? I wouldn't describe it as a singleton because I don't think that I ever heard about the term singleton being used in terms of services. And I don't want to imply that this manager cannot be scaled, because it can. So if I would say singleton, that could be a confusing word from my perspective, because some might consider that, I don't know, if I say that manager is only one, then you cannot scale it, which is not the case. You can do horizontally scaling on the manager as well. But if you want to say that if it's only one kind of manager for the specific Saga, then yes, this is true. So you have one application managing the statuses for all the services in a specific Saga. And you can have, depending on how many Sagas you can have one application, and I actually do recommend that for your entire system, that you scale whenever is needed, and that orchestrates multiple Sagas in your system. But nobody says that you cannot have different managers for specific Sagas. And I think this is really dependent on what your system does, and it's not something I could say it's better or not in the majority of the cases to use one approach or another, because I guess it really depends on, even more than the architecture itself, it depends on your the way your team work, how many teams you have there, how did you separate your responsibilities, if you have or not boundaries, and so on and so forth. So probably with the system growing and having more microservices, then you, of course, it would be more difficult to have only one service that's orchestrating that's managing the orchestration of all the sagas, and you might want to split its responsibility as well into multiple services that do that. But the idea of the Saga is the same in this case. So you said that usually the manager is implemented as a queue or top or queue. I said this implemented with queues or with topics. Queue with topics is not something that sounds well for me, because the destinations when you discuss a messaging system are either queues or topics in case of a JMS, or it's called only a topic approach. In a topic destination in Kafka, for example, you don't have queues, but you manage the behavior of queue or topic by making the groups of consumers. But that's for somebody who knows how Kafka works. If you don't know how it works, don't stress now. You don't need to understand it now. So what information is being held in the queue? That is the question. In the queue, in this case, or in the topic, depending on how you implement it, you would have the status of the specific operation for that service. So you would have A telling I did manage to commit, everything went fine, and I went with no exception, and I delivered my responsibility now further to B, where B needs to do something else, I don't know what, and my status it's still in progress because we didn't finish the use case, but I finished my job. And then it delegates to B, and then B can do the same thing, and then if the manager finds that all the services managed to do their work and they encounter no problem, then it considers the Saga to be complete, and everything is nice because now you have all the data consistent and the operation went well. But it might be that one of them, like B in this case, it fails, and then it will tell M back, hey, it didn't go well for me, I encountered an exception, please do whatever you need to do so that you make sure the data remains consistent. And then what M does is makes sure that all the other services, like A in my case, reverts their changes, and then the Saga is considered failed, and of course the failure and the exceptional reason for the failure can then be logged so that somebody can see what the problem was and investigate it and solve it. I don't know if that's the case. So does A wait for B's response in the topic? Not necessarily. Basically, in case it depends on what kind of Saga. So let's take them one by one. If you don't have a manager, then A might wait for a response for a time, but you might implement it to not necessarily wait for a response. But if B simply sends back to A that it didn't go well with a specific case, then A will simply do the revert operation for that specific case. And when you have a use case, what is a good thing to do is, of course, identify somehow the entire Saga. So I didn't say that, maybe it was a good thing to say it. When you have an execution of a use case, it's always good, and that even doesn't matter if it is implemented with or without a distributed transaction scenario, or with or without a Saga, you always need to have an identifier for a specific use case. So even if you simply have no distributed transaction, I still do recommend you have a unique identifier for a call, and you will find out that in applications sometimes I would say it's recommended in all the times you have tooling to trace a specific call that goes throughout multiple services, so that you can see that a call from A went to B, and for B to C, and from C to D, and everything went well, or something didn't go well. And that's only possible if you identify the flow with a unique identifier, so that you know a specific call on D was done as part of a specific use case execution. So you can identify that which was the call did by A that's part of the same execution, use case execution, as the code that that D has done. So for all operations, with the exception of the cases, and I forgot to say that because I was focusing on only two examples, in a real world scenario, you will have also services where you don't have a mutation operation. So now imagine you have another service here that A calls first to get data, to get the user data. In that case, when you only have a fetching operation and no data is changed, of course you don't need to have any rollback operation because you didn't change data. So you will see that maybe out of 7 services, only maybe 3 of them represent mutation operations. Only for those, of course, you need to have revert operations. For the others who are not changing anything in their own persistence layer, then for those you don't have any reason and anything to do in terms of reverting data. Otherwise, yes, for all the changes that represent, for all the operations that represent changes, you need to do rollback operations. What can be an exception to that is, because we always have exceptions, because that's why software architecture is difficult in general, is when you have when you have a situation where you don't care about the inconsistency, because that can be the case. So say in my case, just say that the fact that I decrement the inventory is not a problem. And because, say, in case of payments, sometimes they might happen to fail, but in my system, maybe it fails 1 at 1,000 requests. And then I always have some kind of a person responsible to the inventory who takes care of the inventory and sees these kind of problems and can manually adjust them, because that's the way my system works. Don't ask me why would someone manually adjust them and not automatically, but say that's the scenario. If that's the scenario, then of course you don't implement a rollback operation just because your business runs in a different way. Because software architecture is always linked to the business, the business use cases that we implement. So it will always be a decision and compromises made there between the complexity you add to the system versus the way you have to solve specific use cases from the business point of view, and of course or together with how the system is deployed and how the developers work, what's the working approach. They are all linked together one to the other, and I think I said that in one of the previous episodes as well, that they are not independent. The way you deploy your application is highly coupled to the architecture, is highly coupled to the way developers work, it's highly coupled to the business you implement. And that's an important thing to understand prior to that. So you will always have exceptions where you can say, in my Saga, for this step, I don't want to have a rollback operation. Not because I don't want to have a complete Saga, but because if I create inconsistencies in this database, they won't affect that much, or they won't affect the business at all. Because say this is only some kind of forecasting database, and in the forecasting database I anyway work with probabilistic numbers, and then one or more products won't affect my calculations. And if that's the case, then of course you have that kind of service that does, I don't know what, calculates I don't know what statistics, and if decrementing the inventory and having a Saga failed here and now and then doesn't affect really the business, it affects the numbers, but the way it affects them don't matter, then of course you will choose not to add that complexity to the system rather than adding it for no value added to your system. So you always need to think about all the corner cases and all these scenarios. When we refer to a pattern in general, in either software development or software architecture, always remember that a pattern is usually a guideline. So it's not a protocol, it's not something that tells you exactly how to implement something, it's a guideline. And the guideline means that you have to inspire from it, but you need to be flexible. And that's what makes software architecture difficult, because if we had a set of rules and we knew these are the rules, just apply them, then software architecture wouldn't have been difficult at all, isn't it? You just learn that set of rules and you apply them based on your scenario. But that's not the case. That's not how software development and software architecture works. That's what makes it difficult. So how does the rollback operation know what to decrement? Does B tell it? So when we have started the use case, as I told you, you have an identifier. So you know precisely what A knows precisely what has done for that specific operation. So for that use case, that use case meant for A decrementing the inventory. And then in the Saga, you associate the operation, the go operation with a revert operation. So for a go operation, wherever applicable, you would always have a revert operation, a rollback operation. So then when B says, in case of the use case with this unique identifier, I failed, whether it goes through a manager in case of the orchestration or directly to A with a choreography approach, B tells, okay, I failed in this case. And in that case, A registered that it did the decrement the inventory operation. So then it immediately finds out what the rollback operation is, if it has a rollback operation for that, and it applies the rollback operation. So that's how it goes. Of course, how you implement that, like how you like program that, you have you have probably an infinity of ways to implement this. But from the architecture point of view, that's basically what you need to do in terms of implementing a Saga. Is there existing implementation for Saga in Spring Framework? Not from what I know. I mean, not something out of the box. You have to implement it. And moreover, I'm not quite sure if you could implement something like that, just because, as discussed in one of the in the previous episode, microservices, one of their characteristics is allowing you to have polyglotism, which means that you might have not only a different platform completely and a different language here, but a different persistence layer as well, which means you might have A implemented with Spring and B with Python, and then things might go totally different from if you have Spring with, I don't know, a SQL database rather than Spring with a NoSQL database. So there are so many alternatives that having a framework for Saga, for me it looks very complex, or a very complex idea. I don't say that I wouldn't like to see that. I'd be actually glad to find something like that, but up to now I didn't use something like that with any of the technologies I've been using, Java or not. So that's the idea of having a Saga. When you have a two-phase commit, as I said, you have all of them basically doing their stuff, and then they commit in the end. All of them, they put up a message, I did it, and then when everybody did it, then you might have also here, say, a choreography, an orchestration approach with a manager telling them, now you can really commit because everybody has done it. But in that case, in the case of the two-phase commit, you might also have the situation where the second commit doesn't work for a reason or another, and that makes it a little bit more difficult, because in that case you don't have a way out. In case of the Saga, you might have also the situation where the rollback operation doesn't work. But usually if you use a messaging approach, then you still have the message there in the queue, and the service, if it's a problem with the service, the message in the queue won't be actually consumed until the operation is actually done, and then this makes it a little bit more robust in terms of implementation with a Saga rather than a two-phase commit. So yeah, that's basically the difference. I do recommend the Saga rather than a two-phase commit. Out of my experience, I don't like distributed transactions with two-phase commits from this point of view, but I don't want to say that there isn't any chance where you won't see that or you won't use that. Some code snipped. Maybe we can try to work some example, even though it would be quite difficult, and I'm not sure that even with a two services example and a very simple one, we would be able to make it in 1 hour. But I promise I will think if I can find an example and try to implement it, or at least maybe implement it prior to our lesson, to our episode, and then show it to you instead of writing it together, because sagas, they might look simple, but they are tricky, and trust me, they are complex. Even for two services, you might find out you spend a lot of time to implement it. So try it as homework if you'd like, and I will also think about this if I can actually implement one prior to the episode so that I can show you an implementation. That would be really nice probably. But try it yourself, try to do this thing. Have a database, MySQL one. Have some very simple database only with a name and an inventory, and you do increment or decrement the inventory. And you have this use case based on two applications. And you make this payment throw an exception. See if you can implement it yourself and how difficult it is. And you will probably find out it's more difficult than you might have imagined, even though it looks simple. Cool. Now, and this is just how to implement it. We didn't actually discuss everything I wanted to discuss, and I would like now to have a much more complex than implementation itself of the distributed way of keeping data consistent. I would like to discuss the issues, the consistency issues that can appear in multiple transactions or multiple distributed transactions that can run at the same time in your system. I'm not sure if you have seen this coming, but this is one of the most difficult. So once somebody learns how to implement what a Saga is and how to implement it, and they say, oh, that was not really difficult, isn't it? I thought this was difficult, but it's not really difficult. Then usually the next thing I do is I introduce the complex stuff, which is what happens if you have more sagas running at the same time, which might make the things more difficult. And let me tell you why. So I'll say consistency problems, consistency concerns with distributed persistence layer. So this is quite a nice subject, but a difficult one. And let's see what we can take out of it. But I think before going into distributed transactions, say testing Saga would be difficult. I do agree. Now, what I do with testing, I do test them service per service. So instead of trying to test the scenarios, like I have an entire use case and I try to test it head to feet, what I do is I test in isolation if this works correctly when everything succeeds, and if this works correctly when something doesn't go well and it has to do the revert, and then I test the same thing for this one, and I do the same thing for each service in isolation. So to simplify my testing for the Saga, I usually apply testing of services in isolation rather than testing the integration between the services. In this way, I somehow minimize the number of tests and I get from my perspective, maximum value out of the tests. That's my opinion, of course. I might be wrong, but usually it costs very much to implement integration tests on the Saga, and that's why, from my experience, the most economic way of doing it is testing the services in isolation. Okay, now back to our discussion. So consistency concerns. Before going into distributed transactions, I'd really like to make sure that you remember which are the consistency concerns for only a simple transaction, only having two transactions at the same time on the same service. So just for the moment, let's step back and think on only one service instead of thinking at from the multiple services point of view. Let's go back to one service and let's consider we don't have a distributed transaction, we only have transactions. Which are the problems when you deal with transactions running in parallel? So these are the problems that are in regards to the isolation, the transaction isolation. And I can tell you we have more than three, but these three are probably the most relevant: dirty reads, repeatable reads, and phantom reads. And these three problems that can appear with having only simultaneous concurrent transactions on a same service, they are the same that can appear when you have a distributed transaction, whether it is or not a Saga. So let's see what these are step by step, and let's see how can they appear on a single service as well as when you have a distributed transaction. And you will see that if on a single service the concern is a little bit more easier to address, because you can use a different isolation level to manage that. In terms of multiple services, it becomes a little bit more complex because you need to apply locks. Generally, you need to apply locks to escape one or another of these problems. So dirty reads. Let's take them one by one. So what a dirty read is. Assume you have two transactions that I will here represent with two arrows. They are nothing more than my temporary axis, so it's a time axis, and you can imagine what happens here, what can happen here if you change a table. Say my inventory table, say I have 10 books, and I do have to change it to 9. So I initially had 10, then I do change it to 9 at some point on this transaction, because one of the books has been taken from my inventory. And then what happens now is the question. If the second transaction here reads the inventory, so we have two in parallel. One of them is this TA or whatever you want to call it, and the second one is TB. So if this, we have now multiple possibilities. If you have even with a non-distributed transaction, if you have what we call read uncommitted setup for your transactions, then what happens is that TB, which is the second transaction here, will be able to read the 9. So what's the problem with that? Well, the problem is that the first transaction now, it didn't end yet. So that means at some point it might encounter a problem and roll back. And if it rolls back, guess what happens here? Well, it goes back to the value the inventory had at the beginning of the transaction, which is 10. But this second transaction TB already read the 9, and instead of using the 10, we'll use the 9. So this is what we call a dirty read. And this is something that can happen in case you apply an isolation level that is called read uncommitted, even if you have only one service. But it's something that can happen also when you have two sagas running at the same time. Because say you have two sagas where you have the A and the B, decrement the inventory and make the payment, and you have the two of them running at the same time, and one of them fails when making the payment. When you have decremented the inventory on both, isn't it? So if the inventory was 10 and they are at the same time, it might happen that both of them will decrement the inventory and then one of them fails. And the one that read the inventory, the one that read, the second one that read, first read the 9, and it will decrement it even further to 8. So now if the second one commits after the first one applies the rollback, instead of having a 9 back, you will still have an 8. So that's a problem, isn't it? So that's something that can happen, dirty read, when you have a saga. And I'm not sure if I've been explicit enough, but if you want, I can actually make a graphic out of it to be more explicit, to see how this can happen. So maybe it's better to do that. So I say TA and TB, and I say TA here, so the first saga decrements the inventory, and then if it decrements the inventory from 10, it will go to a 9. It's basically the same thing you see here for two transactions on the same service, but now they run in between two different services. So now say that the first one read the value, the second one reads the value, it will definitely read a 9, and it will try to decrement to an 8. If the rollback of the first one happens now and it goes back to 10, but the second one already read the 9, it will override the 10 with an 8. So even though TA correctly applied the rollback on the saga, you will still be into a situation where you get inconsistencies. So that's a quite difficult problem. And that applies to all the problems you see here, the concerns on the transaction isolation, which is dirty reads. It's probably the easiest one to explain and observe, but we have repeatable reads and phantom reads as well that I will explain them further. You can have the same problems occurring with sagas, because at the same time sagas are nothing more than operations that change persistence layers and the order in which you execute them might come with different outputs. And you know that when you have multi-threading, a multi-threaded architecture, which is the case here, but it's at the level of a system, then the operations, the order in which they happen on different threads is not guaranteed unless you do synchronize them somehow. And to synchronize them here, because you can't simply just use a synchronized word as in the case of threads in a specific service, here you can synchronize them by simply locking the persistence layer. So you can apply locks to the persistence layer to make sure that if one service did some change, it will unlock that only when the whole saga ended. And the locking itself, now I go back to the first question I got in the today's episode, can be done as well in two ways, the optimistic way and the pessimistic way. But the optimistic and pessimistic locking and locking in general and the transaction isolation, it's something that will take a little bit more than 5 minutes to explain. And yes, now I can answer you and answer also the first question here. Should we use pessimistic locking in distributed transaction? The answer is yes, sometimes. It might be helpful. It has its own advantages and disadvantages. And in the next episode, we will discuss optimistic versus pessimistic locking and which are the advantages and disadvantages, so that you know which are different scenarios where you should apply them to solve consistency concerns of multiple distributed transactions running at the same time. So with that being said, I hope I made also a good introduction in what we need to work on in the next episode, where we will take all the transaction isolation problems and see how they behave and see how can we solve these transaction isolation problems when you have only one service by applying different isolation layers, and then when you have distributed transactions by using optimistic or pessimistic locking. What if we increment or decrement the value in the BigQuery level, like update table set call value +1? So of course the way you implement the update can be, you might have different ways which are better than the others. I will here not try to tell you how to implement this stuff. These are only some theoretical examples, and as I stressed also at the beginning of our episode, and I will do that in the next episodes as well, I don't necessarily choose here the best implementation approaches. I choose the right ones for my scenario to work for my explanation. So yes, in that case, maybe when you say I set a value +1, then that won't happen anymore because I don't read anymore the value or something like that. I will consider clarifying this as well when we discuss the isolation problems. But what I want to make sure is that you understood that here I choose my examples such in a way in which I can explain you the topics, and not necessarily I choose scenarios that are very close to real world. Sometimes doing that is impossible because in the real world we have complex scenarios, and what I prefer to do is to minimize the complexity so that you can understand first what is going on, and then based on what you understood apply it on more complex scenarios as well. Otherwise, if I take it from the complex directly, it might be, or I might risk to lose you rather than help you understand this. And my purpose is not losing you, is helping you understand the examples. That's why I taking them from this simple and that sometimes look like less real world scenarios, but I will always tell you where these things apply in real world scenarios. Uh, and with that being said, the hour already gone. I don't even know when this hour passed, and I think we discussed a lot of interesting things. Thank you very much for being here with me again, and I hope to see you in the next episode when we continue the discussion on the problems of data persistency. And I can't wait to finish with this discussion on data persistency, because the next thing I'm going to discuss after we find out everything we need to know out of fundamentals from the data persistency is going into my favorite subject, which is security, where we have a lot of things to address, including OAuth 2, OpenID Connect, using static key, asynchronous, asymmetric and symmetric keys, and so on. But in the next episode, we are still on the data consistency. Yes, up to that point, thank you again very much. Have an excellent time for study further, and see you in the next episode. Cheers, everyone.